Welcome to ODB AWS Adult channel. In this video, I will walk you through common ODB network topologies using AWS Transit Gateway or AWS Cloud WAN in combination with Transit VPC. Then we will go through a hub-and-spoke configuration, step-by-step setup with a dedicated Transit VPC. And finally, we will summarize the sanity check useful to troubleshoot your setup. My name is Giorgio Bonzi and I'm part of the Oracle Database AWS Black Belt team in EMEA. Let's start with the main use cases for a hub-and-spoke topology. In all of them, the key element is a Transit VPC paired with the ODB network and connected to the rest of networks, internal or external to AWS, through a Transit Gateway or a Cloud WAN. The first use case is cross-VPC connectivity, where one or more application VPCs need to reach the ODB network. On the right side, we have the ODB network. Next to it, we have a Transit VPC with a transit subnet in the same availability zone of the ODB network. This Transit VPC is connected to the ODB network through an ODB peering. The Transit VPC is also attached to AWS Transit Gateway or to AWS Cloud WAN. The application VPCs are attached to the same Transit Gateway, so their traffic can reach the Oracle database at AWS. For simple application to database traffic, direct VPC ODB peering is usually better because it provides lower latency and cost-effective setup, especially now that ODB multiple VPC peering feature is supported up to 45 VPC. Hub-and-spoke is useful when you have more than 45 VPCs to peer or when traffic inspection is required. As in this second use case with additional firewall VPC. The idea is the same, but all traffic passes through an inspection layer before reaching the ODB network. For many internal AWS workloads, direct ODB peering is enough and gives better performance and cost. But if traffic inspection is mandatory, this design gives you a controlled path. The third use case is cross-region connectivity. Applications in one region can connect to Oracle Database AWS in another region by using Transit Gateway peering or an equivalent Cloud WAN design. The local setup remains the same. The ODB network is paired with a Transit VPC with a subnet in the same availability zone of the ODB network, and the Transit Gateway exchanges traffic between regions. The most common use case is hybrid connectivity, where traffic comes from on-premise or from a client network outside the company AWS organization. The external network reaches AWS through Direct Connect or VPN, and then traffic goes through the Transit Gateway or Cloud WAN and through Transit VPC into the ODB network. In this example, external traffic also goes through a firewall VPC, and internal application traffic to the ODB network can still use direct ODB peering to reach the ODB AWS databases. Before we build the configuration, let's review the Transit VPC prerequisites. A VPC that is paired with the ODB network and is used as a Transit VPC must meet three rules. First, it must be in the same AWS owner account as the ODB network. Second, it must have only one Transit Gateway attachment. Third, that attachment must include only one Transit VPC subnet in the same availability zone as the ODB network. These are very important prerequisites, so let's look at these rules visually. In this example, the ODB network is created in the ODB owner account. The ODB network is tied to one physical availability zone, in this case availability zone A. When we add the Transit VPC, it must be created in the same ODB owner account. In the example, the Transit VPC has three subnets across three availability zones. The second rule is about the Transit Gateway attachment. This Transit VPC must have only one attachment to the Transit Gateway. And the third rule is the most important one for this attachment. The attachment must include only one subnet from the Transit VPC. And that subnet must be in the same availability zone as the ODB network, in this case subnet A. For that reason, we recommend using a dedicated Transit VPC. Keep it small and simple. In many cases, one subnet in the ODB network, one subnet in the same ODB network availability zone is enough. You can also use a smaller CIDR range, for example, a /27 or /26. This kind of configuration reduces misconfiguration risk and makes operations easier. So, a dedicated Transit VPC with only one subnet in the same availability zone of the ODB network. Now let's move from the concepts to the actual setup. In this demo, I use an application VPC as a spoke network, but the same logic applies to an on-premise or other external networks. For the hub, I use the AWS Transit Gateway. If you use AWS Cloud WAN, the logic is similar. In some designs, you may use Cloud WAN and Transit Gateway together, especially when you use the Cloud WAN network function group features. This is our starting point. On the right, the ODB network in physical availability zone 6 in North Virginia. The ODB client subnet is 10.87.0.0/24, shown in blue. And in the upper right corner, the Transit VPC, TTT VPC01, with CIDR range 10.40.0.0/24, that has just one transit subnet defined within this Transit VPC in the same availability zone of the ODB network. And associated with this transit subnet, there is a route table, this route table. On the left, we have the spoke network, that is an application VPC, TTT VPC02 with this CIDR range 10.43.0.0/24 and 3 application subnets in 3 different availability zones, all associated to the same route table, this one. And in the center, we have the Transit Gateway that at this point has an associated route table that is empty. The first step is to configure an ODB peering between the Transit VPC and the ODB network. During peering setup, you can select the Transit subnet route table, this one, and then AWS Automation will add for you a route to the ODB client subnet through the ODB network ARN. If the route table associated with the transit subnet isn't specified at this stage, it can be added later using the appropriate AWS CLI command. The peering operation also adds the Transit VPC CIDR range, this one, the 10.40, to the peered CIDR list of the ODB peering setup, this one, to enable the return traffic from the ODB network to the Transit VPC. So at this point, the Transit subnet can reach the ODB client subnet. To test this first step, you can launch an EC2 instance in the Transit subnet, this one, and use an IP address from the Transit subnet, this IP address, for example, in this case. And from that EC2 instance, test the connectivity to the database network. For example, connect to a VM in the ExaDB VM cluster or to an autonomous database endpoint. After this first connectivity test, the next step is to attach the VPCs, the transit and the spoke VPCs, to the Transit Gateway. We need 2 Transit Gateway attachments, this one and this one. The first connects to the Transit VPC, and this one, super important, must include only the transit subnet in the ODB network in the same availability zone of the ODB network, this one. And it must be the only transit gateway attachment to the Transit VPC. The second attachment connects to the spoke VPC and can include the spoke subnets where you need connectivity. In my case, I have configured all the three subnets here. After the attachments are created, the Transit Gateway route table receives propagated routes for both the VPC siders, the spoke and the Transit VPC, through the respective Transit Gateway attachment. Next, we need to add the VPC route table entries that allow the Transit VPC and the spoke VPC to reach each other through the Transit Gateway. So I add this route here to reach the Transit VPC schedule range through this Transit Gateway attachment, and the same I add to the Transit VPC route table, the Transit VPC subnet route table, this entry to reach the spoke schedule range through this attachment. After that, they can communicate in both directions. And again, we can test the spoke to transit path, launch the test EC2 instances in the spoke VPC, for example in these two subnets, and reuse the EC2 instance that we used before. And test connectivity from the EC2 instances in the spoke subnet to the EC2 instance in the transit subnet. Alternatively, you can also use AWS VPC reachability analyzer. At this point, the spoke VPC can reach the transit VPC. The remaining task is to route traffic from the spoke VPC all the way to the ODB client subnet. And to complete the forward path, we need to add two routes. First, in the spoke subnet, here, subnets, route table, we need the route to the ODB client subnet through this transit gateway attachment. And second, in the transit gateway route table, we need to add a static route to the ODB client subnet through this transit gateway attachment, the transit gateway attachment to the transit VPC. And the transit subnet route table, this one, already includes the route to the ODB client subnet through the ODB peering that has been added before. The last step is the return path from the ODB network back to the spoke VPC. And to do that, you need to add the spoke VPC CIDR range, the 10.43, to the peered CIDR list of the existing ODB peering connection, this one. Important, add this CIDR range from the ODB peering connection dashboard, not directly in the ODB network. And now the full routing setup is in place. The ODB network, as you can see here, knows how to return traffic to the spoke VPC through the transit VPC. And we can now test end-to-end connectivity from the EC2 instances in the spoke VPC to the ODB network. If all routes and prerequisites are correct, the connection should work end-to-end. This is the final design. The spoke VPC reaches the ODB network through the transit gateway, the transit VPC, and the ODB peering connection. But let's finish with a troubleshooting checklist. These checks are useful when the routing path does not work as expected. First, confirm that the spoke CIDR is added to the ODB peered CIDR list. Second, check that the transit subnet route table has a route to the ODB client subnet with the ODB peering ARN as the next stop. Third, make sure the transit VPC attachment includes only the transit subnet in the same availability zone as the ODB network. Fourth, confirm that the transit VPC and ODB network are in the same AWS owner account and that the transit VPC has only one transit gateway attachment. Fifth, validate the transit gateway route table. You should see routes for the transit VPC, the spoke VPC, and ODB client subnet. Then check the spoke subnet route table. It must include a route to the ODB client subnet through the spoke VPC attachment. And finally, if you are using Network Function Group Cloud WAN feature, add a Transit Gateway in the middle due to the static route Cloud WAN limitations with Network Function Groups. We are at the end of the video. To summarize, we covered the main use cases, the Transit VPC setup, and the most important troubleshooting checks. The main takeaway is simple. Keep the Transit VPC dedicated, align the Transit Gateway attachment with the ODB network availability zone, and always check both the forward path and the return path. I leave you with the links to the public documentation and YouTube video post related to DNS configuration for Oracle Database at AWS. Thank you for watching and see you in the next episode. Bye.